So this is part of the project, as was mentioned before, efficient smartphone sensor analysis for behavioral profiling in transportation research, a case study of driver and passenger classification. This is the agenda. We are going to go over this today quickly. So here, this is the introduction. Then we are going to go over some related work, the methodology that we use, some results and analysis, practical implications, conclusions, and references. We are going to go more in detail in every section. So this is just like a brief overview. First, introduction and motivation. We know that smartphones are everywhere, and of course are packed with a lot of sensors, including motion sensors, location sensors, etc. And this makes the smartphones ideal for passive, low-cost data collection. So for accurate classification of driver versus passenger behavior, this can be helpful for enhancing the in-vehicle safety, so to suppress the distractions for drivers only, for example, or to improve behavioral modeling for traffic flow and travel behavior studies, and also enable insurance telematics. That's some work on this has been done before. There is also a growing demand for intelligent transportation solutions that calls for methods that can passively profile the user behaviors in real-world environments. These systems that also for systems that are efficient enough for mobile deployment. So as cell phones specifically or smartphones are very well adopted and everybody is working on them. So we are also worried for this part of the, we need to preserve the battery, we need to preserve the resources that are limited, right? So this brings us a question that is, can we accurately classify drivers versus passengers using a short burst of natural smartphone sensor data without disrupting the user or without overwhelming the device? So that's the question that we started, we have in mind to follow the next steps. After reviewing some of the current work or previous work, we have some challenges. We found some challenges. So for example, some other related work have some behavioral assumptions. Most of the prior studies that we found, the smartphone is carried in a specific location. So I put it in a pocket, in a trouser pocket, in a carrying some specific hand, or require the user to perform a specific activity, like walking to the vehicle, like start a text or something like that. Another challenge is that there are pre-trip sensing overhead. So some of the systems that we found initiate the sensing before the trip begins, so require continuous monitoring to know when the user walked to the car and when the user opened the door of the car. So those movements are, or some kind of micro movements need to be detected, and that requires continuous continuous sensing, which of course increase the amount of resources spent by the device. Another challenge is the inflexibility and resource waste. It was mentioned like that because those techniques involve custom subroutines or extended activity checks. So also the other part was some limited naturalism, because few students really allowed users to interact with the phone, with their devices as normally would. They require the user to do some specific activities, have some specific behavior. So all this is part of the challenges that current approach have. What is the gap then? So there is a need for a method that avoids rigid assumptions, that minimize energy use consumption, and works under natural unconstrained mobile usage. Therefore, here are our research objectives. So our research aims were twofold. The first one, we aim for a naturalistic classification. Then we need to evaluate the feasibility of distinguishing between drivers and passengers using a smartphone sensors data collection without usage constraints. We want to avoid usage constraints to make it naturalistic. And also, we want the users to interact with their phones as they normally would, encouraging natural device handling. The second objective here was be conscious of the resource of the system. So when we design a system, we need to be conscious of we are dealing with a device that has limited resources. And for this objective, we explore techniques for deploying mobile classification models in a way that is mindful of a smartphone resource limitation. And we have emphasis on reducing battery consumption and computational burden for long-term real-world use. So based on those research goals, we have some tasks. The first task was, we defined the first task, short time windows analysis. So we need to decide, or we need to find if we can use a small time frame windows. Can those windows capture enough data for reliable classification? Then for this, we have the task was to evaluate different time frame windows. I'm going to explain what I mean by time frame windows later. The second is a classifier performance. In this case, we evaluate 3 machine learning models: decision tree, random forest, and support vector machines. Those are commonly used in this kind of data that we are dealing with. And they also are well suitable for the data sample, data size, so we can evaluate information in a suitable way for those machine learning models. The preprocessing techniques, then that's normally part of a very important part of evaluating a machine learning model. Which data are we feeding the model? So we thought those preprocessing techniques are also sometimes expensive. Then we want to evaluate how effective are they. If at the end we can decide which one is the best to use. Then we assess, in this case, feature standardization, feature selection, and dimensionality reduction as those preprocessing techniques. And practical deployment relevance, we examine how results can support passive data collection. So there is one specific example with one bus away. Here's some related work what they have done before again, but that's more specifically on working with driver passenger classification. Those most of them are using sensor-based detection, right? This is some reference for some authors that have used accelerometer, gyroscope, magnetometers, inertial sensor, etc. for this task. But most of them also have used machine learning models similar to the one we decided to try in or test in our experiments. The only one that we didn't use was a CNN from this review. Behavioral triggers and activity detection. So system often initiates sensing during specific activities, like walking into the vehicle, reading messages, entering from a particular side. Some of the previous work, like it needs to detect if the person is entering from the left door of the car, from the right door of the car. So they are interacting with other hardware too. Assumptions are about phone placement. I mentioned that before. Many approaches assume that the phone is in a trouser pocket, handbag, or mounted in a fixed position in the car. And report what other studies have reported in accuracy. Prior studies have reached high accuracy, between 85 and 95%, but under controlled conditions with constraints, uses patterns. So these are like previous words specifically that have been used this. Which constraints then we found? Again, rigid device placement requirements. So per trip activity dependence. I mentioned the previous one before, so that's why I didn't go again. Like we need to be walking, we need to enter steps, etc. We need continuous sensing. They need continuous sensing. That's in those studies. They need reliance on external components. Sometimes you need to communicate with some other device inside the car. Of course, lack of naturalism. This is a table from some previous studies that we analyzed. I'm gonna go over it. No, I'm not gonna go in detail over it, but that's the information I have for those. And here's the contribution versus that prior work. So we're going to work with natural device usage. Unlike prior work, in this study imposed no constraints on phone placement or orientation. So we encourage user to interact naturally with the device. Passive mid-trip inference classification can occur any point during the trip, not just during the entry or the exit. Resource efficient design, emphasis on short data windows, and lightweight preprocessing that makes the system viable for energy-constrained smartphones, and systematic evaluation. We perform evaluation of interaction between classifiers, different classifiers, different time windows, and different preprocessing techniques across 504 experiments, which provide a different insight into deployment strategies. Okay. Let's go over data collection, some description of how we collect data. The study designed, we staged 145 trips around the University of South Florida using short urban style routes. We have 6 volunteers acting both as driver and passenger. So every time a trip occurs, there are at least 2 people in the car. One of them, of course, is driving. The other one is a passenger, and each one has one device that was given to the participants. Each trip averaged 14 minutes, simulating real-world commute, short commutes, of course. And each tour includes multiple trips. So each trip is approximately 4.5 miles each, beginning and ending at USF parking lot. So to the right, we have like a description of the routes. The goal for this is to capture high-frequency motion data under natural conditions with minimal control or intervention. These are the devices used for data collection. Diverse mix of Android smartphones were available at the time that we performed data collection. These are Google Pixel 4, 5, Samsung Galaxy S9, S10, and Galaxy S21 5G. And these are the Android versions of that by the time that we were collecting data. These sensors, they describe the sensor type and raw features. So this is our nowadays common sensors available in any cell phone, mostly. So we have the accelerometer that we can collect raw data as timestamps, features X, Y, Z in terms of acceleration on each axis. Same for gravity. We are measuring in all axes X, Y, Z, with their respective timestamps. We have the gyroscope, which is going to measure the orientation of the device in relation of each axis. A magnetometer that measures the magnetic field and helps to identify the magnetic north. Again, is giving us at least three raw values for features, and orientation, which is a virtual sensor that is based on the other sensors that grab data from physical sensors, I mentioned, as I said before, and describe the orientation of the device in a 3D space using a quaternion notation. Continue with data collection overview, then you unrestricted mobile behavior. The participants were instructed to use the device like personal phones. For this purpose, each participant received their phone at least 1 week before data collection. And we suggest the participants to install at least 2 personal applications. In that way, they might be forced in some certain, to say in a way, to interact with the phone often. Then they try to use that phone as their personal device. Ground truth collection, so participants manually start and stop logging at each trip. So the only instructions that we gave to the participants was were like, when you are going to start a trip, you start logging data, and when you finish a trip, you stop logging data using an application called Sensor Logger. The trip events were timestamped and geolocated using Google Maps. And driver passenger status labeled per trip for training and evaluation. So every participant labeled their own data. When they were driving, they labeled their data as drivers, and when they were passenger, they labeled their data as passengers. Next, we are going to talk about feature extraction and data preprocessing. So for feature extraction, what we did is each trip was approximately 14 minutes. So was divided into fixed time windows. I'm sorry, this parenthesis here should go in a previous slide when we were mentioning that this trip was 14 minutes, aligns with national data of 18 minutes for running errands. So in general terms, every one of our trips is approximately 40 minutes long for data. Then what we did was we select 21 different window size, let's say 3 seconds. So if we say 3 seconds, we are going to split that 40 minutes in time frames of 3 seconds. If the biggest window was 90 seconds, so we are going to split 14 minutes in time frame windows of 90 seconds. So of course, the smaller windows are going to yield more training samples. Each one of the time frame windows for each trip is going to be a sample for that trip, which is going to be classified or labeled as a window for a passenger, or a label for a label for a passenger or for a driver. This increased granularity and potential classifier robustness. For example, again, 3-second windows divided into a trip into many short segments, frames of 30 seconds, and a 30-second window will divide exactly the same trip, but in fewer segments. Then we calculate statistical features over those time frame windows. So for each window, which features are gonna calculate? So for each window, even axis, we're gonna calculate the mean, the variance, the median, the minimum, the maximum, the 25th percentile, and 75th percentile. In total, for each sensor, since each sensor produces multiple axes, we're gonna end up with 133 features per time frame window. So regardless of the window size, if it's a 3 seconds or a 90 seconds, each segment is gonna produce 133 features using the same statistical extraction pipeline. These sets remain consistent across all time windows. Why short time windows matter? So this is related with resource efficiency and practicality. Shorter data windows, if we are collecting data, that means we are using the sensors during that time frame window. A shorter window is going to reduce battery usage and processing time, and can also enable on-device inference in real-world apps with limited computing power. Aligned also with mobile sensing, like there is specifically Android has something called activity transition API that can be used as a trigger for a short burst of data collection. So the core idea here is if short time frames are effective, we can balance accuracy with energy and efficiency. Continue with preprocessing techniques. We use or we evaluate the standardization. Standardization, as you probably know, it scales the features to have zero mean and unit variance. So this is going to prevent that if we have a large numeric range of data in a time frame window, we can avoid that those large values to dominate the learning process. It's relevant to this study because standardization was evaluated for its effects on classification accuracy. And it matters because, as I said before, some machine learning algorithms are sensitive to feature scale. But also, standardization adds computational cost. So we want to evaluate, do we want standardized or not? So we need to evaluate that if it's worth to keep it or not. The next preprocessing technique, feature selection. Feature selection identifies and retains only the most informative features, those with higher variance. Because if we have low variance, that really don't provide enough information to the machine learning model to take decisions. So this process is basically discard features with low variance. Why this matters? Oh, I'm sorry. And this assumes that the features are going to contribute little. The ones that we remove are not going to contribute with the classification process. Why does this matter? Because this reduces model complexity and computational load, the health balance, accuracy, and efficiency. The third slide here for processing techniques, pre-processing techniques, dimensionality reduction techniques. We evaluate three principal component analysis, kernel PCA, and random projection. Different than feature selection, these techniques reduce dimensionality by projecting original features into a lower dimensional space, but then it's going to change actually the feature. It's going to change the value. It's going to reduce the dimension, but it's going to change the value. So this is not always desired, but it depends. It can affect the accuracy. Why it matters? Because reduce processing and memory demands for resource-constrained device and can mitigate overfitting when the sample size is small relative to feature count. Okay, so that was, we went over the design. We went over data collection. Now we're gonna check the design of the experiments. So we used three machine learning models: decision tree, random forest, support vector machine. These are besides they are widely used, they have some specific purpose. But random forest, for example, is a very robust and it can be very useful for improved generalization and reduce overfitting. Support vector machine can be very useful when the sample size is not big, is relatively small. And then in this case, when we have long time frame windows, like the longest one we have was 90 seconds, the number of samples was reduced. So that it makes work to try to evaluate a support vector machine in that case to see if that there was a good fit for that. Random forest is based on assembling of decision tree, which is fast. what we did was a combinatorial evaluation approach. So we make a combination of all the three classifiers, evaluating each of them with feature standardization, with and without feature standardization. And we evaluate also the combination of those two with feature selection and with three-dimensionality reduction techniques mentioned before. So we evaluate that. For example, we have one experiment could be the classifier random forest with data feature standardization and feature selection, or three classifier without data standardization and using one dimensionality reduction techniques like PCA or kernel PCA. This was evaluated across the 21 different time frame windows. In total, with this combinational evaluation approach, we had 504 classification tasks or experiments. And for every experiment, we use a 10-fold cross-validation used for training and testing. Which evaluation techniques we use after each experiment? We use accuracy. This is the percentage total of instances correctly classified. Precision is percentage of predicted drivers that were actually drivers. And recall, which is a percentage of actual drivers that were correctly classified. So why these metrics? They provide a balanced view of both model correctness and risk, especially relevant in transportation safety context. Now let's go over results and conclusions. So we find out that shorter time windows consistently improve classification accuracy. As the window size decreased from 90 to 3 seconds, accuracy increased across all classifiers. So for example, in the case of random forest, that was overall the best classifier during the experiments with using the standardized features. It went from 0.87 to 0.97. So with using 90-second window, accuracy was 87%. Using 3-second windows, the accuracy was 97%. A similar trend was observed with non-standardized data for most of the models. In this case, the implication for these results is that short time frame windows, we can say between 3-6 seconds, 3-5 seconds, are sufficient and more efficient, ideal for real-time or energy-sensitive applications, at least related to passenger and driver classification. Feature standardization, related to feature standardization, it works really well or improves accuracy, but only for large time frame windows. When we have small time frame windows, feature standardization applying to feature standardization didn't make a big difference. And since that this is a process that can be time consuming, we can consider at some point excluding it to gain efficiency in terms of uses of resources. So for longer windows, standardization features outperform non-standardization by a wide margin. So for example, in 3 for 90 seconds, we have 89% versus 0.49 with non-standardized. In short windows, accuracy with and without standardization was nearly identical. So standardization is beneficial for large windows, but might be unnecessary when the time frame windows are short. Also, related to feature selection versus dimensionality reduction, feature selections outperforms dimensionality reduction pre-processing in most of the scenarios, specifically effective with random forest and tree classifiers. SVM was more sensitive. Feature selection led to lower accuracy actually in terms of for the support vector machine classifier. In this case, related to feature selection and dimensionality reduction, the conclusion that we have was that variance-based feature selection is a strong choice, but particularly for tree-based models. Another result is in terms of effectiveness of dimensionality reduction, performance by method, so with standardized data. So we have the PCA performed overall the best in terms of between the dimensionality reduction techniques. We have a accuracy of up to 95%. Random projection and kernel PCA were less stable, especially with fewer sample or under standardized data features. In conclusion, the PCA is effective when feature reduction is needed, but again, feature selection generally performs better. So probably these dimensionality reduction techniques are not necessary or might not be necessary. These we have different plots. We only select some for the presentation. So in this case, we are presenting data related to standardized data. We have another plot for non-standardized data. This is each line represents each of the preprocessing techniques. So the blue line represents feature selection. The gray one represents random projection. The dark orange one represents PCA. And the light orange represent kernel PCAs. PCA. When you see it here, support vector machine, you see that it behaves relatively well when we have, I'm sorry, on the x-axis here are the different time frame windows. These are not equally, there's not equal space between them. They are just labels. So these are 90 seconds, 45 seconds, 30 seconds. And as we were going down, we were making the gap between the time frame windows smaller. As I was saying, the support vector machine start well because we were saying before the support vector machine works well with a small sample size, relatively small sample size. So they didn't improve very much after that initial high value, getting up to 93 point something percent. I'm sorry, for something. Here we have decision tree that we can compare with the next slide. Here with decision tree, we can observe that feature selection shows a better performance overall over the other reducing dimension techniques. Again, here was the best in this case. Features selection again using random forest. So we have, going back again, support vector machine. We have decision tree, and here we have random forest. So in general, for classifiers, random forest consistently outperform other models. Tree was also strong and more efficient, but still a random forest was better. And SVM underperformed, especially with non-standardized data. In conclusion, random forest for our evaluation for this specific case was the most accurate and robust classifier. This table summarizes 3 time frame windows, 90 seconds, 9 seconds, and 3 seconds. These are not all because there are 21, so we don't have them all. And this basically is telling us on the right side, we have the results for standardized features. On the left side, we have the results for non-standardized features. And each block is going to show for each classifier, starting with decision tree, for each one of the feature selection or the dimensionality reduction techniques. In summary, shorter time windows, approximately less than 5 seconds, around near 5 seconds, provide in these experiments higher accuracy and better efficiency. Standardization, second one, standardization is only necessary for longer windows, but since we noticed that shorter windows are the way to go in this study, then we probably can, we don't need to use them. Feature selection yields the best performance across most configurations, so it is a good tool for use. And random forest is the top perform classifier, followed by tree, and dimensionality reduction works, but is less effective than selection. Implications for resource-constrained devices. Efficient classification will limit the resource. The study showed that short data windows are sufficient enough. That was like the first question. Can we have short bursts of data collection and can be enough to classify passenger vessel drivers? Preprocessing steps like standardization may be skipped for short windows, saving processing time and energy. Benefits for mobile deployment. This might reduce the battery drain. That's a complaint when you are using collecting passive data passively on using applications on users. Complain about battery drain because we are doing shorter sampling periods. Smaller data segments, that we can relate this with low memory and CPU uses, and may enable on-device inference without requiring cloud computing. Application in travel behavior apps. This is relevant to passive sensing system. So in previous projects, we work with one bus away that collects data passively. So that one bus away was collecting, when collect data, it was using the activity transition, the API from Android, and then this can be integrated with application like one bus away by triggering data collection for short periods of time when one specific activity is identified by that activity transition event. And those activity transitions events are already designed by Android, by Google, to be low resource consumption. The short window classifications can be triggered mid-trip using APIs, like I mentioned before. Practical use, apps can classify user as driver or passenger without a fixed phone position. This was also other of the goals, be naturalistic data collection. Also enables activation of context-sensitive features like blocked-in notifications, safety alerts when one passenger or driver is identified. For deployment, real-world use for deployment, we suggest with the data we have right now. Of course, the spectrum is wider than what we evaluate, but for what we evaluated, we recommended favor random forest classifier, short windows, and use feature selection for optimal performance. We can avoid assumptions about phone placements. This is designed for naturalistic interaction. This minimize the sensor use and preprocessing when aiming for real-time classification on a smartphone. And broader impact, this can support transportation research, insurance telematics, and driver behavior analytics. And providing a foundation for a scalable energy-aware classification system. Study limitations, of course, as you can notice, the participation was only 6 users, so this limits so far generalizability across broader populations. The trip types, all trips were short, local, and centered around a single campus. So this is a constraint or a limitation that can be improved. Classifier scope, as mentioned also before, we focus on 3 models, on 3 base models and support vector machine, and we did not explore deep learning also, but sometimes deep learning is a little bit more expensive. So future work, expand participant pool, broaden trip scenarios, longer commutes, different vehicle types, and explore other models. In conclusion, this is short-time windows are highly effective for that case study. Random forest plus feature selection yields the best performance across experiments. Standardization helps in longer windows, but might be unnecessary for short-time frame windows. Shorter windows enable efficient deployment on smartphones with limited results. And the impact is to provide a practical framework for mobile behavior sensing in transportation, supports real-time scalable classification in low applications, low power consumption applications, and offer insights for app developers, transportation researchers, and smart mobility systems. These are some of the reference of the study. The complex list is in the paper that was presented at, this job was presented in TRB 2025. And thank you. I think that's it for today. I'm sorry, I'm a little bit nervous still at the end of the presentation. But
thank you so much, Wilson, for the information. We did, if you would like to ask a question, you do have access to both the chat and the Q&A box. As identified on the screen, we did receive a number of questions during the registration process that I'd like to kind of get to. The first question says, can it differentiate between two people versus one person with two phones?
can you repeat the question again?
Sure. Can it differentiate between two people versus one person with two phones? So if you have two people with two phones versus one person with two phones.
Not really. I mean, at this point, when we have each device, let's call it device, right? Each device is providing a set. So unless you know that the device both device belongs to the same person, the classification is going to treat each device at one data set or one set of data to perform classification, right? So unless that is official, like explicitly mentioned, and each device is going to be considered as a different person. Does that answer the question?
Yeah, I believe that answers the question. Yeah. Next question says, why is it important that this kind of process work under natural phone usage conditions?
Well, it is important because when we are collecting data passively, we try to avoid to first overwhelm the user with instructions, and second, probably most important, is normally users in this kind of passive data collection, they don't want to follow, or they won't follow instructions. At least I'm talking for myself, but we cannot guarantee that the user are surely following instructions to use the phone in a certain manner, unless they are really engaged or have a compromise to do data collection, right? But if there is something like passively, like that's the aim, we should let the user use the phone in a natural way. That's the reason.
Great, thank you. Next question says, what makes feature selection more effective than dimensionality reduction techniques?
Probably we hypothesize that in this case is because feature selection is going to grab information that with high variance, which is the kind of information that provides better feed, better, let's say, food for the machine learning model. So if you have features that doesn't variate across during the time, then basically it's not telling me anything. So, but you have features that are varying, that have a high variance, then that provides information for the model. So this feature selection, that's one of the reasons that can be why it's working better here. And then also on top of that, you are having sensors that are providing high variability, normally like gyroscopes or like accelerometer orientation.
Okay, the next question says, could the findings be used to applications outside of the transportation industry?
Yes, this. I mean, of course, it needs to be adapted, but it can be used for or similar techniques, of course, with appropriate theories can be applied for example, health in monitoring health or mobile security. You know, so that can be also applied in those areas.
Great, thank you. And I did put the evaluation on the screen. If you could take a few moments to complete that evaluation, just either click, you can scan the QR code with your cell phone and or click on the link on the screen. And then the final question says, how do shorter time windows help with resource constraints on smartphones?
Well, so yes, we can relate, as I mentioned during the presentation, that when you have a short burst of data collected, that means we are using sensors during a shorter period of time, that we need to do computations during a shorter period of time with less data. So that's going to improve the usage or the resources, use of resources in a device like a cell phone or smartphone that has constrained devices or limited resources.
Great. Thank you so much. It doesn't look like we have any additional questions. So again, on behalf of the National Institute for Congestion Reduction, thank you so much for joining us today for our webinar. We do have several webinars scheduled. So please feel free to visit the NICER website to see all of our upcoming webinars, view any of our recorded webinars, as well as sign up for our newsletter. Again, so thank you so much for joining us today, and we'll see you all real soon. Bye, everybody.
Thank you. Goodbye.